Morning, ma'am. Thank you for providing us with the opportunity to discuss such an important topic in operating system, which is IPC or inter-process communication. So without further ado, let us just dive straight into the point. First of all, what is IPC? IPC or inter-process communication is a mechanism that allows processes to communicate and synchronize their functions. It's crucial for resource sharing, process coordination, and overall system efficiency. So let's just start with an overview of different IPC techniques. There are several methods available, each with its own advantages and challenges. The main techniques are shared memory, message passing, sockets. Along with it, there are pipes, semaphores, and signals. First, we have shared memory. This technique involves multiple processes accessing a common memory space. It's very fast since processes can directly read from and write to memory. However, it comes with challenges, particularly regarding synchronization and the potential for data corruption if multiple processes try to modify the same memory simultaneously. Next, we have message passing. This technique allows processes to communicate by sending and receiving messages. It's straightforward and ensures safe data exchange, but it can introduce overhead and latency. Especially in distributed systems, message passing is widely used in client-server architecture and other distributed systems where processes need to communicate across different machines. Moving on to sockets. Sockets serve as endpoints for sending and receiving data over a network. There are two main types: TCP sockets, which are reliable and connection-oriented, and UDP sockets, which are faster but connectionless. Sockets provide flexibility and are essential for networking communication, but they can be complex and require careful security considerations. Next, we have pipes, and pipes are just unidirectional or bidirectional data channels that allow communication between processes. They are named pipes, also known as FIFOs, or which stand for first in, first out, and unnamed pipes. Pipes are simple to implement and are effective for communication between parent and child processes, which we include in fork system calls. Next, we have semaphores, and semaphores are just synchronization tools that signal processes to prevent race conditions and manage resources. There are binary semaphores, also known as mutexes, and counting semaphores. Lastly, we have signals. And on the other hand, signals are asynchronous notifications sent to processes to alert them of events, such as interrupt or exceptions. They allow immediate handling of events, but they can be complex to manage and may require signal masking. Signals are often used in OS kernel level, which include ISR or interrupt service routine also. So in conclusion, we can say that IPC is a vital component of operating system, enabling processes to communicate and synchronize their actions effectively. We have explored various IPC techniques, each with its unique benefits and challenges. When choosing an IPC method, it's important to consider the specific requirement of the application we're planning to use. So thank you for your attention, and thanks again.
Good morning, ma'am. Myself Roshan Banerjee, and thanks for providing us the golden opportunity to discuss about the great scientist named John von Neumann. He was born on December 28, 1903 at Budapest, Hungary. He was an Hungarian-born American mathematician. He did his early education from Budapest's most prestigious secondary school. In 1925, he earned a degree in chemical engineering from the Swiss Federal Institute in Zurich. He also enrolled in University of Pázmány Péter in Budapest as an PhD candidate. At the beginning of his professional life, he joined the University of Princeton in 1930 as a visiting professor. In 1933, he accepted a professorship at the Institute for Advanced Study. Now, I would like to say some of his contribution. Between 1923 to 29, von Neumann wrote 6 papers on the set theory. His main contribution to set theory was the von Neumann-Bernays-Gödel set theory, which is essentially an extension of the Zermelo-Fraenkel set theory. He was also proved a theorem known as Minimax theorem for zero-sum games. From 1927 to 31, he wrote 5 papers on a quantum mechanics. Now, in conclusion, John von Neumann was not one of the original scientists tasked with working on the Manhattan Project although he did pay multiple visits to Los Alamos as a sort of consultant. He eventually proposed the von Neumann architecture, which is a type of computer architecture designed to process arithmetic logic. He also created the March shot algorithm, and such the great scientist was diagnosed with what was likely a form of cancer and went to the afterlife on February 8, 1957 at the age of 53. Here are some references from where I have collected the data, and this is my team. Thank you so much for your attention. Thanks again.